Hello, Riles. Let's take a look at lesson 5.6 on the sine law. It's likely a property that you've used since grade 10. We're going to be able to see a proof of it this year. It's not something that you're expected to reproduce, and you will be given a version of the sine law on any quiz or test or culminating that requires it. The sine law uses right-angled trig, but it lets us move outside of right-angled triangles. So let's take a look at this situation right here. It says we have a right angle triangle, an angle of 60 degrees, a hypotenuse of 10, and an angle of 50 degrees here, and we're asked to find x. It says first find the value of the vertical line, probably like the length of that vertical line. Switch that right there. BD. To do that, here, let's just, well, I guess we'll just call it BD. We can set up a sine ratio. So let's say the sine of 60 degrees is going to be the ratio of the opposite to the hypotenuse, BD over 10. In other words, we multiply both sides by 10. We get that BD is going to be 10 times the sine of 60 degrees. We know the sine of 60 degrees is root 3 over 2, but I think a decimal approximation is probably better here. Sine of 60 degrees. There we go, and we can approximate it if we need to about 8.66. We might want to go back and keep it as an exact value a little bit later. So that's 8.66. And now, in this triangle, we should be able to use another sine ratio. The key here is that the height is shared in both of these triangles. It says use the length of BD to find the value of x. So I'll say the sine of this angle, 50 degrees, is going to be the ratio of the opposite, BD, to the hypotenuse, x, right there. If we substitute in our specific value, we see that the sine of 50 degrees is going to be about 8.66 divided by x. Let's try maybe reciprocating both sides. It means that the reciprocal of the sine of 50 degrees is going to equal the ratio of x to 8.66. Then I multiply both sides by 8.66. What you might recognize here is that this is going to be 10 times sine of 60 degrees divided by the sine of 50 degrees. If you're familiar with the sine law, then you can pretty much see it right there. I'm going to write in it's 8.66 divided by the sine of 50 degrees. If I've kept this answer from the previous question stored in my calculator, then I don't need to round it off. I can just divide by the sine of 50 degrees. And I get that x is going to be about 11.3, I think it's centimeters. I can judge for reasonableness. BD would definitely be better, or definitely had better be less than 10 centimeters. X looks like it should be longer than 10 centimeters. I'm not going to assume it's drawn to scale, but notice a larger angle of elevation would shorten that. A shorter angle of elevation is going to lengthen that. So yeah, 11.3 centimeters looks about right. All right. Example number 2 is purely algebraic. What we're going to do is build a version of the sine law here. So it says use triangles ABD and triangles BCD to write two separate expressions for the length of the shared side H. And then I think on this side we equate them. Yeah, we'll do it all on this side and just summarize it on the other side. So here I'm going to say the sine of angle A is going to be the ratio of H to C. That means that H is going to be, multiply both sides by side length C, keep that as lowercase c, give it a little mullet at the back there. We get C times the sine of A. But then in the other triangle, the sine of angle C is going to be the ratio of H over A. Multiply both sides by A to isolate for H, and you get that H is equal to A times the sine of C. So this is going to feel like solving a system through substitution, which we did all the way back in Unit 1. Imagine we're looking at a triangle where we don't even have the height. Well, then we would want to eliminate the heights by setting these equal to each other. Call that statement 1 and that statement 2. We set statement 1 to statement 2, and we get that C times the sine of A is going to equal A multiplied by the sine of C. Now, this is actually a version of the sine law. It's not a very popular version of the sine law. The more popular versions of the sine law would occur if you were to, here, let's split this into two different directions. I'm not sure we need to split. We can just reciprocate. Right, this is angle C right here, that's side length C. Let's see what happens if I divide both sides by side length C, and maybe on the same step, I divide both sides by side length A. If I divide the left-hand side by C, those will eliminate. If I divide the right-hand side by A, those will eliminate. And I'll be left with the ratio of the sine of an angle to its opposite side is equal to the ratio of the sine of another angle to its opposite side. Writing this in English, or reading this in English, is kind of problematic. It basically says that in a triangle, the product of an side length with the sine of an adjacent angle is constant in the triangle. This right here says that the ratio of the sine of an angle to its opposite side length is constant in the triangle. Now we could do another proof of this, turning it sideways, drawing another height, and we would be able to show that you're also able to write that this is equal to the sine of B over side length B. In fact, usually students have some sort of triplet of the sine law memorized or understood. You never need to use two equations at once. You usually don't have this much information either. But it does not matter which letters you have as long as you are working with what's called an angle side pair. You'll only be given one version of the sine law. This is usually best if we're solving for an angle when our unknown is up here in the numerator. We can always reciprocate both sides. It still says that the ratio of a side length to the sine of the opposite angle is constant in a triangle. Something like that there. Okay. The sine law works in triangles that are not right-angled triangles. It will work in right-angled triangles, but it's probably not your go-to method. You should probably use SOHCAHTOA. So, on the back here, written in the general case, maybe we just let go of ABC as well, because sometimes students get a little bit hung up on those letters. Let's just draw a different triangle for ourselves. Let's call it PQR with side lengths of lowercase p. Am I going to make that look scriptive? Mullet, I guess. Q and R. Maybe this capital P should look more capital. Good. In any triangle, the sine of one angle divided by its opposite side length. Geez, I haven't written a scriptive P in a long time. How's that? I don't like it, is constant. So the sine of angle P divided by side length P is going to equal the sine of angle Q divided by side length Q. And if you needed it, you could write is equal to the sine of angle R divided by side length R. Okay, I've seen students stress over, oh, what's A, what's B, what's C. It's more important to look for angle side pairs. Angle side pairs. Okay, to develop an understanding instead of just substituting into formulas. Or the reciprocal version of this. Here, I'll just even switch the order around to show you that it doesn't matter. The ratio of R to the sine of angle R is equal to the ratio of side length P to the sine of angle P, which is equal to the ratio of Q to the sine of angle Q. Let's talk about common errors. Sometimes students forget the sine ratio in the sine law, which is kind of embarrassing because you need the sine ratio in the sine law. Other mistakes occur when students don't have things lining up. Notice that in this version up here, up in my numerators, are the ratios of angles, and in the denominator are the sides. That has to line up. I can't have angle side and then side angle. Over here, sides in the numerator, ratios in the denominator. I guess one other mistake I've seen happen a couple of times is students use the cosine ratio accidentally. But, I mean, it's called the sine law for a reason. Let's try out two versions of it. In our next lesson, we are going to discover that there are some problems with the sine law. These examples that I've given you do not have any problems. Okay, so you might be a little suspicious when after today's lesson we see that there are some hiccups. Example 3 says, find the length of side C in the following diagram. If I want this question to go as fast as possible, I'm going to figure out what side length C is. It's AB right here. Okay. Now, I can use the sine law when I have an angle side pair. I'm not set up for the cosine law, which we haven't reviewed yet. This is the only side that I know, which means that to use the sine law, I would need to know this angle right here. And I'll give you the sine law formula. What I'm not going to give you is a reminder that you know the sum of the interior angles of a triangle. So I think first what I'm going to do is say angle A is going to be 180 degrees minus 48 degrees minus 25 degrees. Of course, I'm going to label what I'm looking for, and I'm going to show my calculations so that my reader knows what I'm doing. I'm presenting a solution. 107 degrees. And now we have what is called an angle side pair. I have an angle side pair, which means I can use 25 degrees to find side length C. I generally don't find that students need to write down the formula and then substitute in. I think if you understand how the sine law works, you can set up a proportion. My advice is put your unknown, the thing that you're trying to find, in the top left. Top is definitely best because then you won't have to reciprocate. Left is usually where we want to solve. Put your unknown there. So if I put side length C there, I need to compare side length C to the sine of angle C. And in this side of the proportion, I need a side length up top and the sine of its corresponding angle. I don't know this side length, so I'm not going to use that. I know this angle side pair. I put 36, technically it's centimeters, up top, and the sine of 107 degrees in the bottom. Right. The sine of 25 degrees is just a number, but I'm not going to bother approximating that now. I'm going to undo a division by the sine of 25 degrees by multiplying by the sine of 25 degrees on both sides. Solving for a side length with the sine law, there's absolutely no problems, even at the grade 12 level. So I'm just going to reach for my calculator now and type in 36. I can do this in a couple of different ways. I like doing 36 divided by the sine of 107 degrees multiplied by the sine of 25 degrees. I can check my answer for reasonableness. I'll round it off to the nearest tenth. Should be in about centimeters. I mean, it looks okay. It's quite a bit smaller than 36 centimeters, but 25 degrees is quite a bit smaller than 107 degrees. The other way of typing this in, maybe multiply first and then divide. Let's try 36 times the sine of 25 divided by the sine of 107 equals. And yeah, I get the same answer. Okay. You cannot use SOHCAHTOA here because you don't have a hypotenuse. You don't have, if you're focusing on, say, this angle as your angle of focus, you have two adjacent sides. SOHCAHTOA will not work because we're same with circumflex. Okay. This isn't standard position. Let's try one more that might not have been in our original package because we want to practice. We can use the sine law to solve for a side length or to solve for an angle. Once in a while, you might have to draw your own triangle. Don't worry too much about drawing it to scale, but it will help in the next lesson if you spend a little bit of time trying to draw it to scale. I'm given a triangle GHI. I'm told that angle H is 120 degrees. So I'm just going to spend a bit of time trying to get like 120 degrees about right. Yeah, that looks fine. 120 degrees. That's angle H right there. I'm told that side length H is 12.3 centimeters. So I'm going to label that right there. That's 12.3 centimeters. It doesn't really matter which side is G. I'm just going to decide, I guess. If I make this side length G, 9.1 centimeters, that makes this angle G right there. And I'm asked to solve for angle I. So they're making this almost as hard as it could be. I'm not in a right angle triangle, so I can't use Pythagorean theorem. I can't use SOHCAHTOA. I don't have enough information for the cosine law, which we haven't reviewed yet. I do have an angle side pair. Okay, with an angle side pair, I can use this side to solve for that angle. Well, we might pout here and say, well, that's not the angle that I want to find. I want to find angle I. I'm going to calm down a little bit and realize that if I use the sine law for angle G, then I can just use the angle sum of a triangle theorem to find angle I. So there's my plan. I'm ready to go. I'm using the sine law, so I set up a proportion. G, angle G is going to be my unknown, so I'm going to write the sine of G in the top left. And I'll write that the sine of G ratio to the side length 9.1 is going to be equal to the sine of 120 degrees to 12.3. Notice we shouldn't be saying, okay, so like G is A and side length G is side length A. You don't want to memorize sine of A over A equals sine of B over B. It should be fluid kind of thing. I have one ask of you here that's going to help us a lot in our next lesson on ambiguous cases. I want you to approximate this ratio. Okay, I need you to just trust me now that approximating this ratio is going to be useful. I'm going to type in the sine of 120 degrees times 9.1 divided by 12.3. I'm going to write that down. In previous courses, maybe you would have been taught to just take the sine inverse of that without writing it down, but we will find some uses for approximating this ratio to like 4 decimal places. Approximate your ratio before invert signing. Before inverse sign. Okay. The problem is there might be more than one solution to this equation, and seeing this ratio is going to help us spot. There can't be in this case because of the obtuse angle, but we'll explain it later. Just trust me for now. Take the inverse sine of that angle, and we get G is going to be about, usually go to the nearest degree here, 40 degrees, I suppose, for G. When you think you're done, maybe take a look at your diagram, reread your directions. We were asked to find angle I. We don't know angle I. Oh, I see how I'm going to get angle I. You might be able to do this calculation in your head, but tell your reader what you're doing. 180 degrees minus, 40 degrees minus 120 degrees. That's 160 degrees, so angle I is about 20 degrees, like that. Okay? Every sine law that you've done in the past, including these two, probably are triangles that have only had one solution. We're going to see later that in a specific situation, there could be more than one solution. It's another case where our calculator isn't going to tell us all the answers that we're looking for. So be ready for that in the next lesson.